Hello, hello everyone. Today I'm going to talk about infinite sets and just sets in general. Okay, this is a very mathsy topic, and me being a physicist, it's not my favorite, but there's lots of cool stuff you can enjoy. But yeah, potentially. I think a mathematician would do a better job than me describing this topic. But well, let's see how it goes. Okay, so sets and subsets. So subsets are quite intuitive. So, for example, uh, humans are a subset of animals. Is a subset of animals. Basically, any human is an animal. Okay, so if you take animals, and humans, that means if X belongs to humans, then X also belongs to animals. That's the definition of a subset. And okay, you can have, depending on the number of elements in the set, you can have different subsets. So, for example, if you have a set containing 3 elements, A, B, and C, the subsets are all the possibilities. Well, we start with the empty set, then just A, B, C, then A, B, B, C, and AC. And of course, the set itself is a subset. So A, B, C. So these are all the subsets of this set. Is that making sense? Is there any questions here? So how many subsets? Well, in this case, it is 8. What is the link between what is combinatorics? Yes. What is the link between the number of elements and the number of subsets? It's 2 to the power 3. Boom. Yes. Ooh, Abiola. Yes, you've done an extra step there. Yeah, absolutely. It's 8 is 2 to the power 3. So there are 2 to the power n subsets of a set of cardinality n. Cardinality n. Okay. 2 to the power n subsets of a set of cardinality n. Okay. Ooh. Maintain connection is unstable. Right. So problem 2, I took example 4 from the assignment, and it said, which of the following diagrams define maps? So a map is just like a function. Like you've done functions in school, and you know that a 1-to-1 is a function, many to one is a function, one to many is not a function. So here, this is not a map because, first of all, the element 57 doesn't have a corresponding value in the set X, and the number 9 is mapped onto two different numbers, 5 and 7. So this is a one-to-many, which is not a mapping. This is not a mapping. Oh, this is. This is, no, sorry. 57 is not an argument. You have the number 9 corresponds to two different values, so no. Now, for the second one, this is not a mapping because the number 11 does not have a corresponding value in the Y set. There are no such limitations in. No, a function doesn't have to be continuous. For example, there are examples of functions which are discontinuous at every single point. Let's talk about this because I think we'll have some time. Okay. No, and this is not a mapping because the number b is mapped onto two different values. So no, that's a one-to-many. We're not allowed one-to-many. And here, this is a mapping because every value of x has a corresponding value in y. This is a many-to-one. We don't have to use all the values in y. There's no limitation on that. So that's a yes, that is a function. That is a mapping, map, or if it was just numbers, it would be a function. But a mapping is just a more general way it's a more general thing, right? It could be a mapping can link a set of, I don't know, a set of jelly babies and a set of, I don't know, what else can you do? Frogs, chocolate frogs. I don't know. I started watching Harry Potter. I watch it every Christmas. Right, so let's talk about continuity. That's because that's an interesting thing. So this is a little bit of sidetrack, but continuity. A function is called continuous. F of x is continuous at point x0 if the limit of x tends to x0 of f of x is equal to f of x0. That's the definition of continuity. And a function can be discontinuous at certain points. For example, examples of discontinuity. So the sine function, f of x, sine function, sine of x, it is defined as 1 if x is greater than 0. It is defined as 0 if x is equal to 0, and is defined as -1 if x is less than 0. This is the sine function. And if you draw a graph of the sine function, so it's 1 here, it is -1 here, and it's 1, 0. So this is an example of discontinuity. This function is discontinuous at x equals 0. This is a discontinuity of a second type. A discontinuity of a first type would be like this. So for example, f of x equals x minus 2 squared over x minus 2. So this is a function that is continuous at every single point except the point 2, where the function doesn't exist. Okay, x minus 2. Yeah, so that's this. Yeah, would be like this. You know what? I'm just going to do plus 2 here so that it's a more. Okay. So the function doesn't exist at 2. But if this is a discontinuity of the first type, why is of first type? Because all I need to do is just redefine f of 2. So I would say this is when x is not equal to 2, and it's 2 if x is equal to 2, and I have removed my discontinuity. So this is a removable discontinuity. So all I need to do is define the function at a single point, and then the discontinuity goes away. So it's a removable discontinuity. Continuity is the first type, and this is second type. It's unremovable discontinuity. And finally, I promise to show you a function that is discontinuous at every single point. And then I can show you a function that is discontinuous at every single point except 1. Okay. First, the Dirichlet function. I don't know how to spell Dirichlet. Just not to embarrass myself, I would just say a function that is discontinuous at any point. Okay, so f of x is 1 if x is a rational number, and it's 0 if x is an irrational number. Let's call it irrational like this. Irrational. So you can imagine what this function is. So it's sort of, because there are infinitely many rational numbers on any interval, so it would be like but then there are infinitely many irrational numbers as well. So limit, there's no limit. Limit of x tends to x0, f of x does not exist. Does not exist for x, for any real number. For any real number, the limit doesn't exist. So the function is discontinuous. The function has a breaking point at every single point, which is quite cool. The second type which is a continuation of this function. A function is discontinuous at any point except one. So let's do this one as well, and then we'll move on. So tool. Okay, I'm finally excited about this topic. Okay, so f of x is x if x is rational, and it's 0 if x is irrational. So you can imagine that it's a very similar function, except it goes like this, and then like this. And then you can show that the limit of x to the power 0, f of x, is the same as f of 0. Therefore, continuous at x equals 0, which is quite cool. Right, so, okay, sorry for the sidetrack. Problem 4 from the assignment. I'm not going to do the whole thing, but I'll just show you how to do this. Or have you all figured it out? Have you all figured out how to do question 4? Okay. So it's not really complicated. You just need to understand what you need to do. So basically, g of f, you just need to draw the possible one. So gf. So first you do f, and then you do g. So it would just be 1, 2, 3, 5. And here, so you first do f, and then you do g. So 1 goes to 1, and 1 goes to 137. So 1 goes to 137, just like that, etc. So this is A. B would be HG. So you do G 0, 1, 2, and then you do 137, but then you do H, which is 1, 2, 3, 5. So you just need to do this, etc. Any questions? I hope that makes sense. Okay. All right. So countable and uncountable sets is the next part, and Aleph node. So cardinality is just the number of elements in a set. And by definition, so we define the cardinality of the natural numbers n. And we say the cardinality of n is Aleph node. Aleph node. Aleph. Aleph node. So what does that mean? That means that there are n the number of natural numbers is Aleph node. Of course, there's infinitely many natural numbers, but if you can make a bijection, that means a one-to-one correspondence between another set and the set of natural numbers, we say the cardinality of that set is also Aleph node. Okay. So if you can if you can make a bijection one-to-one correspondence, one-to-one mapping from set A to the set of natural numbers n, then the cardinality of A is equal to Aleph naught. So do you understand what it says here? On a scale of 0 to 10, please. What about the other two people? Okay. Oh, yeah. All right. That's good. So basically, what you can do? Well, you can do whole numbers, right? You can, if you make a one-to-one if you make a numbered list of all the numbers, that means that they have the same cardinality. So, for example, the number of there are as many integers as natural numbers. There are as many integers as natural numbers. A nonsensical is a statement that sounds nonsensical, but is in fact true, because if you say these are the natural numbers, 4, 5, and if you are able to make a one-to-one correspondence between the set of the natural numbers and the set of integers, then there means they're the same. Basically, if you can number them all, that's called a countable set, and a countable set has the same cardinality as, has cardinality Aleph naught. Okay, so the integers are 0, minus 0, 1, minus 1, 2, minus 2, 3, etc. So you can make a correspondence, a one-to-one map between the set of natural numbers and the set of whole numbers. Therefore, the cardinality of the whole numbers is equal to the cardinality of the natural numbers, which is Aleph naught, which basically means, aka, Z is a countable set. We don't consider 0 as a natural number, right? No, just natural is 1, 2, 3, 4, 5. Sometimes people say there's natural numbers, there are whole numbers, and then there are integers. But I find this disturbingly, I find that really disturbing. Why would you expand the definition of natural numbers just to include 0? Whereas you can say just Z plus positive whole numbers. Well, 0 is not positive. Okay. Yeah, that's what I thought. I'd never used Z plus. I used just natural or whole numbers. So I don't know. I don't like complications. I would just say if I want negative numbers, yeah, I would say Z minus. If I want positive or zero, I would say natural or, well, I would just say z, x, and x greater or equal 0. Just that. That would probably be the easiest way of, rather than inventing 7 different ways of writing the sets. Okay, now countable sets. So the set of even numbers is countable. So even numbers is countable because you can, if you write down all the even numbers, 2, 4, 6, 8, etc., you can correspond it to 1, 2, 3, 4, 5. You can enumerate them. So therefore, you can make a one-to-one correspondence between them. So even numbers. The set of even numbers has the same cardinality as the set of natural numbers, which is again Aleph naught. The interesting example is the rational numbers. So two statements that seem absolutely nonsensical. Between 0 and 1, there's infinitely many rational numbers. And that's very easy to show. For example, you have 1/2, 1/3, 1/4, 1/5. Like all of these are rational numbers. They're between 0 and 1, and there's infinitely many of them. However, the cardinality of the rational numbers is the same as the cardinality of the natural numbers. Even though there are infinitely many rational numbers just between 0 and 1, the number of rational numbers is exactly the same as the number of natural numbers. Maths is weird. And to show that, the number of rational numbers, all you need to do is just to organize them properly. One way how to do this is you can make them into rows and write them out. For example, 1 first, 2 first, 3, 1, 4, 1. Then you could do -1 over 1, -2 over 1, -3 over 1, -4 over 1, etc. Then you have 1 over 2, 2 over 2, 3 over 2, 4 over 2, etc. And then you can do, well, -1 over 2, -2 over 2, -3 over 2, -4 over 2. Oh no, it's 1/2. Then there's 3 over 2. So these are all rational numbers. Rational, do you remember the definition? A number is rational. X belongs to Q if X is M over N, where M is an integer and N is a natural number. That's the definition of a rational number. Rational. So basically they're all fractions. Oh yes, miss one. Okay, just write 0 here. And then just start numbering them. How can we number them? Making sure that we don't miss any single natural number. Yeah, zigzag, of course. You can go 1, 2, 3, 4, 5, 6. Now 1, 2, 3, 4, 5, 6. Now we already had 2 over 2 because it's 1 over is the same as 1 over 1. So skip that. So 7. Then 8, 9, 10, 11. We already had this one. 12. Oh, we already had this one. 12, 13, etc. So you just keep going, skipping the ones you've already counted, and that means you have written down all the rational numbers, which are fractions, and yeah, so that's that. The statement, yes, I'm corresponding every rational number to a natural number. Did I say whole? Did I say integers? I meant natural. So every fraction has a corresponding natural number, and every natural number corresponds to a fraction. And we listed all the possible fractions. So that's it. Okay. Yeah, is everyone happy with that? Do you understand? Yeah. Okay. Now the problem 5, I mean, you probably have seen it. You probably will see this 5 or 6 times in your life again. My experience with this question is that I've done this question when I was at university. I've done this question when I was a teacher. I've explained it to people. I think I understood it maybe 2 years ago, like properly. I properly understood this statement, even though I did it. So I'll do it just one more time. Yes, this is a diagonal thing. Base 10. Yes, never made sense doing in base 10. Yeah, in binary it makes so much more sense. Yes, but yeah. So show that the set of the numbers from 0 to 1 is uncountable. Well, that means we cannot make a correspondence. Okay. We will go from we will do a proof by contradiction. Proof by contradiction. Imagine or assume we managed to number all real numbers from 0 to 1. Okay, so if the first number, the second number, the third, well, just simply A1, A2, A3, A4, A5, etc. So A1 would be something like 0.0000000, probably just zeros, because it's the first number and it's infinite. The second number, point something. So let's not without any specifics, but let it be 1, 4, 9, 6, 1, 3, 2, whatever. There's infinitely many of them, so it doesn't really matter what I write. 0, 3, 2, 6, 1, 3, 9, 2, etc. 0.889777, 0.333667, right, etc. Now, so we have a full list. We have a full list, and if the list is full, that means we can't write down a number that is not on the list. We can't have a number, so any real number would match one of the numbers on the list, okay? And I will show you that this is not true. So start constructing a number A, oh, just call it B. What I'm going to do is for this number, I'm just 0, because obviously it starts with 0. I'm going to take the first number, the first digit of the first number, and change it by 1. So I'm going to do +1, so 1. From the second number, I'll take the second digit, and I will change it to the next digit, which is 5. I'll take the third digit from the third number and make it into a 7. I will take the next digit from the fourth number and make it into an 8. And then I'll take this fifth one and make it into a 7. Now, if I encounter a 9, I just make it 0, etc. So what did I just achieve? Well, because the first digit is different from the first number, that means B is not. So this 1 means that B is not equal to A1, because it has the first digit is different. The second digit is different from A2. That means B is cannot equal to A2. The third digit is different from A3, so B is not equal to A3, etc. So B is not equal to AI, where I is any natural number. So B is different from every single number on that list, which contradicts. Okay, I'll just write B is different from any number on the list. Therefore, contradiction. Okay. How well did you understand this? How well do you think you understood that on a scale of 0 to 10? Okay. All right. Okay, so not only it is uncountable, but the number of elements on the set can there exist an uncountable set in an accountable set? No. No, if you have any subset of a countable set is countable. Any subset of a countable set is countable. Yes, definitely. Not only the real numbers are uncountable. The set of numbers from 0 to 1 is uncountable. The set of the set of numbers from 0 to 1 has the same cardinality as the real numbers overall. Okay. There are as many real numbers on the interval. The cardinality of the real numbers such of the real numbers from 0 to 1, there are as many real numbers on the interval 0 to 1 as there are real numbers on the interval. From minus infinity to infinity, to plus infinity, which is quite interesting. Now, how to prove that? So let's take the interval from 0 to 1, 0 to 1, and just bend it. Bend it into a semicircle. Yeah, a function of tan pi x minus a half. Why would you use minus a half? Oh, minus. I just use arctan. Oh, okay. Let's translate. Okay. Yeah, you can do that, and you can do that on the yeah. But I'll just show you a one of the methods, one of the hundreds of methods. So if I bend that interval from 0 to 1, and now I take the set of real numbers. So this is the number line, x number line. Now if I draw a point here, so there's a point somewhere on the interval from 0 to 1, and if I draw a straight line, it corresponds to a single point on the number line. So point alpha corresponds to a number beta. Any number from this, any number alpha from 0 to 1 has a corresponding beta from minus infinity to plus infinity. And then, yeah, so you can see that any number on that interval has a corresponding value on the number line. All right. So yeah, thank you. Yes, I like that proof as well. Alpha 1, beta 1, alpha 2, beta 2, etc. Beta 3, etc. Okay. Same cardinality as the set of real numbers. There's a few a few interesting things we can do is that we can show that that there are, yeah, so here I can say that the cardinality of the real, well, let's call it, let's give it a name. So A is the set of real numbers such that x is real and x is on the interval from 0 to 1. Okay, let's just define that. So the cardinality of A has the same cardinality as the real numbers. And we call it, well, sometimes they call it aleph 2 or 2 to the power aleph naught. Aleph naught. So this is the cardinality. And we can show that the cardinality of the real numbers is the same as the cardinality of infinite sequences of zeros and ones. And some of you have already done that. So infinite sequences of zeros and ones. So let B be infinite set, set of infinite sequences says of 0 and ones. The statement, the set of B, the cardinality of B is equal to the cardinality of the real numbers, which is equal to 2 aleph naught, simply means that any real number can be written in binary. Okay. Any real number can be written in binary. So let's show that. And it's quite an interesting one. So there are multiple different methods, and if you do computer science or anything, you probably know the floats and how they are recorded in computers. Now, floats are obviously not infinite, but let's say we want to make a correspondence between every single real number on the interval from 0 to 1, because that's easier, and a binary number. Okay. Imagine we have an interval from 0 to 1. And we have a real number. Let's say write x equals 0.78732 blah 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 in binary. We know how to write natural numbers in binary, right? I don't need to explain that. Natural numbers in binary, just binary numbers. Like 3 is what is 3? 1 1. 7 is 1 1 1. Okay, in binary. So that's easy. But what about real numbers? Like, how can you write an infinitely long number in binary? That doesn't make any sense. Well, didn't make sense to me. But still, you have infinite decimal points. Even if you do standard form, you have infinite decimal points. What do you do with the infinite number of decimals? Well, there's one method. So what we do first, we split the interval in half. And if it's to the left of that number, we write 0. And if it's to the right of the middle, we write 1. So for this number, this is 0.78, so it's going to be 0. Oh, we can write 0 just to indicate. Yeah, because it's 0.0. Now, oh, sorry, 1. What am I doing? 0 point. So the first number, if it's to the left of the midpoint, it's 0. If it's to the right of the midpoint, is 1. Now we take the midpoint of the right interval. If it's to the left of that, we say it's 0. If it's to the right, we say it's 1. So that would be 1 again, because 0.78 is more than 0.75. 0.5. Then we split that into half again. So that would be that 3/4, that would be 7/8. If it's less than 7/8, is on the left, is 0. If it's more than 7/8, it's on the right, it's less than 7/8, so it's 0. And then you carry on, and this way you can find what you will, what's it called? You will diverge, or you will diverge onto that number. So this is quite a clever. Did you understand this method? You split the interval in half. If it's on the left, you write 0. If it's on the right, you write 1. And this way you can find any single point. How would you find it bijective? Because only if you follow the rule, if you follow the ones and zeros, that will bring you to the if you follow the ones and zeros, that will bring you to the real number. And if you follow the real numbers, you will end up with a unique sequence of ones and zeros. So any sequence of zeros and ones will bring you to a unique real number. Yes, there are rough edges, and unfortunately, I don't know how to resolve the rough edges. But I won't talk about this in a second. We'll bring you to a unique real number. So any sequence of ones and zeros and ones, and we'll bring you to a unique real number. And any real number will result in a unique sequence of ones and zeros and ones. So there is a problem. The problem is that the borderline cases. So 0.5, 0.75, 0.25, they don't work. So we have to exclude them. But yeah, there's this is a countable set. This is a countable set that we can exclude. I don't remember exactly how you exclude it, but this I just wanted to show you the method. In a similar fashion, and if you take all the sequences of ones and zeros, if you take all the sequences of ones and zeros, so this is a countable set. This is countable, so it has the cardinality is aleph naught. But then how many different ones do you have? Well, each has two possibilities, so 0, 1. So the number of strings of possible possibilities, so that means it's 2 and 0 possibilities. And that is also equal to the cardinality of R. It's just cardinality of R. Because every digit has two possibilities. So every digit has two options. Therefore, there's 2 to the power aleph naught possibilities, which is also equal to the cardinality of R, which is quite cool, right? Okay, I think I've spoken about everything I wanted today. I can take some questions if you have. If not, happy to set you off and tell you to enjoy your holidays. And those of you who are doing interviews, has anyone had their interview yet? Okay, Monday, nice. Right. Did it go well? With mapping like this, could you say that the sum of all R is 0? So there's a question with a mapping like this. Could you say that the sum of all R is 0? Well, the problem with infinite. The problem with infinite sequences or sets, they can lead to different results. Like if you do, let's take the sum of all integers. Is the sum of all integers 0 or not? 0, no 0. Well, let's see. We can write 0 plus 1 minus 1 plus 2 minus 2, of course. So that is decisively 0. Well, what if I go differently about it? What if I do 0 plus 1 plus 2 minus 1 plus 3 plus 4 minus 2 plus 5 plus 6 minus 3 plus 7 plus 8 minus 4. This is just a for instance. So here we have, if we break them down into triplets, this is 0 plus 2 plus 5 plus 8 plus 11, I'm guessing. So that is obviously infinity. What are you going to do about it? Okay. All right, I had mine this Monday this week. I think so, the conventional for math interviews, they were all questions on. They were all questions on a personal statement. Oh wow, that's surprising. They threw me off at the start. I think mine was good too. Yeah, and it can be -1/12 as well. You can rearrange them. I don't remember exactly how you do this, but you can arrange them. All right. Okay, well, that's good. That's great. Great to hear. We do have a nice record of COMPOS students. Half of COMPOS students went to Oxbridge. Ah, maths. Maths. Nice. Excellent. Ah, okay. So you're going to be colleagues. Yeah, perfect. All right. So I'll see you. I'll see you in the new year. Of course, we have a guest speaker. A guest speaker in on the 18th. So that's 6 days from now. Next. Sorry, is it the 19th? I think it's the 19th of yeah, it is the 19th. Sorry, next week there is a webinar by guest speakers from Faculty AI. So there will be 3 short lectures and a Q&A. So I understand that they will be talking about AI, of course. Yeah, so please do come. We have sent an invitation to everyone. I'll see you. Say half of COMPOS students getting into insane statistics. It is. I mean, it was the first cohort. It was 60 students who got it to the end of COMPOS, and 30 of them went to Oxbridge. We don't have the statistic for the second cohort, and you are the third cohort. So let's see how it goes. Enjoy. Well, yeah. So see you. I won't be there next week. I just won't be lecturing. So I'll see you next week. And if I don't, see you in the new year. Bye.